This is Lab 4, Oscillations by James Ashbaugh. As an introduction, in this lab, I analyzed data and video observing a mass in oscillatory motion suspended by a spring and influenced by the force of gravity. The purpose of this lab is to understand how oscillatory motion works about energy and to also properly implement computational models to compare experimental data versus predicted data. The underlying physics principles that go into this lab are understanding different energy graphs and how to calculate various types of energies, such as gravitational and spring potential energy, and also kinetic energy. Furthermore, this lab used the position and velocity update formula to update information about an object's motion. As a brief preview of my results, I discovered that my computational model more accurately predicted the motion of the suspended mass than the tracker analysis did. Also, the graphs displaying different types of energies, x position versus time, and y position versus time, all displayed oscillatory characteristics. As a setup of the experiment, I identified the system as the mass, spring, and the Earth, and everything else as the surroundings. The initial conditions for the experiment are that the mass was released at an initial trajectory. The force of gravity and the spring force began to act on the mass instantaneously. For the experiment, this snippet of code represents the iteration component of my computational model. The total energy of the system is calculated from adding all of the individual energies together. The net force on the mass is also calculated. Finally, the position and velocity of the mass are updated every time step. Furthermore, this is the output from running the code from Web v Python. The bottom two graphs demonstrate an oscillatory pattern of motion for the mass in both the x and y directions. The top graph shows that the total energy of the system remains constant. Finally, all other energies exhibit an oscillatory pattern. For my results, the predicted versus observed data regarding the mass's motion matched closely. There were slight deviations in the graphs which were caused by different sources of error. Here are some possible sources of error that could have occurred during the tracker analysis. Firstly, there could have been recording errors, such as possible misclicks on tracker analysis. Also, I could have not adjusted the frames correctly at the beginning and end of the video, causing the experimental model to be slightly off from exactly matching predicted data. Secondly, I could have made mathematical miscalculations, mathematical errors in calculating the initial position and velocity, which would alter the predicted data from the computational model. So what does it mean? Is the energy principle satisfied? Yes, because there is no work being done externally on our system. The total change in energy throughout should be zero, which it is. For the period of oscillation, the x position versus time period is 1.71 seconds, while the y position versus time is 1.519 seconds. They are pretty similar, but there is a slight difference because force of gravity is acting on the mass in the y direction. Because this lab had no what-if question, I asked, what if the spring had an increased spring constant? The motion in the y direction would be much more restricted due to the spring being more rigid. Therefore, the amplitude of the y position versus time graph would be much less. Also, the change of position of the mass in the x direction would also be less, because it is more restricted. Overall, a mass attached to a vertical spring experiences oscillatory motion in both its position graphs and energy graphs, but the change in total energy remains constant, and oscillatory motion can be predicted very accurately using computational models. Thank you.